This video is part one of a few videos that are going to be used to compile sections 4.2 through 4.4. So we're going to combine three sections here as a means of, I think that all fits together good enough this seems to be the way to go about doing this. So hopefully it's not too much. We will take a few days to cover the material, but this video should cover what you need for those sections. So we're going to be using circles here. Sometimes the unit circle, which means a radius of 1, to determine trig values. And so we have to recall from previous classes we've learned about SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. For any right triangle, that works. Well, we're going to introduce here the inverse functions. The inverse of sine is called cosecant. And up here I showed the abbreviations. These are the names of the functions: sine, cosine, tangent, cosecant, secant, and cotangent. Please do not say sin, cos, tan. They're called sine, cosine, tangent. I just kind of cringe when people say that. And then cosecant, secant, and cotangent. In blue here are the definitions. These are inverses. So the cosecant is the inverse of sine, 1 over sine, and that becomes the reciprocal of this. So instead of opposite over hypotenuse, becomes hypotenuse over opposite. Secant is the inverse of cosine, and cotangent is the inverse of tangent. You can see those there. So here's an important thing that I want to demonstrate. This here I wrote sine of an angle is equal to cosine of 90 minus that angle. So basically what that means, if I take the sine, and right now you'll notice in my calculator here, I am in radians. I'll go to degrees. I'll change that back in a minute. But for the sake of argument, let's pick an angle and take the sine of it. Like, let's say I take sine of 70. Sine of 70 is that decimal there. Well, what's 90 minus 70 in order to the complement of that? Well, the complement is 20 degrees. So the cosine of 20 degrees should be the same exact thing, and it is. This works for any angles, and it'll work for radians too. But let me demonstrate another one here. So if I do sine of, say, 50 degrees, all right, there I have, now I'm in degree mode. That's why this is working. I'm not in radians, I'm in degrees. So the sine of 50 should be the same as the cosine of what? You guessed it, 40. Now why is that true? First off, the reason we want to look at a triangle, a right triangle, and when I draw a right triangle with, of course, a 90-degree angle in it, let's say I'm talking about this angle here as my theta. Well, that's going to be the opposite. This would be the adjacent, because it's next to it, and the longest side is always called the hypotenuse. So if I'm here, and by the way, this one over here would be 90 minus that, because the three angles have to add up to 180. This one's already 90, so I know these two must add up to 90. So if I'm looking at it from here and say the sine from here, that means opposite over hypotenuse. That means this bottom side over that. Well, from here, we would call that cosine. From here, this would be called the adjacent over hypotenuse. And so that's a demonstration of why this is true. Now, if I had changed over to radian mode, all right, now you'll notice that sine of 50 and cosine of 40, oops, let's go back up here. They're not the same things anymore. That's because 50 and 40 radians are not complements of each other. I might have to do this in terms of pi, for instance. So if I say, what's the pi of 3 pi, I'm sorry, that's not what I wanted. Let's back arrow here. What I meant to say was pi over 3. You got to remember what pi over 3 is. Pi over 3 is the equivalent of 60 degrees. Well, that's complementary with 30 degrees, which is pi over 6. And so here I should get the same decimal there. So I'm demonstrating that this is true, but if you're using radians, we got to make sure we're in radian mode there. Okay, on to the circle here. This circle, what this is demonstrating is anytime that we have, and I want to add, I forgot to add this line here, and this one. So this is a circle centered at the origin, and the triangles that I have drawn in there represent multiples of 45 degrees. So you'll recall from the previous section, this is 0 degrees in standard form, 45 degrees, 90 degrees, 135, 180, and so on, all the way around the triangle. So if we're dealing with a multiple of 45 degrees, or that's the same thing as pi over 4 radians, I want you to really keep in mind that that's pi over 4 radians, we're going to land on one of these locations if we're doing any multiple of 45 degrees. So to demonstrate how we use this circle here to help us out, first off, over here I've written the 45, 45, 90 triangle in the smallest form here, 1, 1, and square root of 2. And you can see over here on the circle, if I'm dealing with a 45 degree angle, or pi over 4 radians, and I want to evaluate the sine, the cosine, the tangent, or any trig function at that point, well, I use a point on this circle to help me out. And so when I put this thing inside of here, I go, okay, this is 45 degrees. I draw the 45, 45, 90 triangle, and I say, all right, the sine of this angle right here, this is the one, we're going to call that a reference angle. We're always going to use angles that are touching this x-axis, and you'll see that as we go on here. But what's the sine mean from here? Well, the opposite is 1. The hypotenuse is square root of 2. So I get 1 over square root of 2. But we got to rationalize that. We can't leave a square root in the denominator. So I get the square root of 2 over 2. That's the same thing as the sine of pi over 4, because pi over 4 and 45 degrees are the same things. So I'm going to demonstrate that real quick just to reinforce that a little bit with you. Right now the calculator is in radian mode. So if I type in the sine of pi divided by 4 in radians, that's an angle written in radians, we know that's the 45 degree angle. That number there is what you would get if you typed in the square root of 2 divided by 2. Let's show that. Square root of 2, we'll close those guys, divide by 2. It's the same decimal. Now if I convert or change this over to degree mode, I can type in that same problem, except instead of saying sine of pi over 4, it's going to be called 45 degrees, but I'm going to get the same decimal. All right, so hopefully that makes sense. And by the way, let's talk about multiples of pi over 4. So let's say 45, this is 90, 135, 180, and so on. Well, if we count in terms of pi over 4, and I call this arc here, this is the pi over 4, this is 2 pi over 4, which is pi over 2, here's 3 pi over 4, 4 pi over 4, which is pi, here's 5 pi over 4, 6 pi over 4, here's 7 pi over 4. So we can quickly find sine, cosine, or tangent of any of these. So let's just take, for instance, 3 pi over 4. The sine of 3 pi over 4. We're going to use this triangle right here, because we're going to go, okay, 1 pi, 2 pi, 3 pi over 4 is right here. We draw in the 45, 45, 90. However, note a few things here. The hypotenuse, when we do this hypotenuse will always be positive. You will never make the hypotenuse positive. So this one here, I forgot to write it, but that'll be square root of 2. But the sides of the triangle, the other sides, the legs, are going to either be positive or negative depending on what they would be if you were plotting this point. Well, if I was plotting that point, I would go left and then up, which is why I have a negative here and a positive here. If I was plotting this point down here at 5 pi over 4, I would go left and down. That's why both of these guys are negative. If I was plotting this point over here, I would go right and then down, which is why this is positive and that's negative. And first, if I was plotting this one, I would go right and up. They're both positive. So to evaluate the sine of 3 pi over 4, which is here, I use this angle now. This is my reference angle. And I do sine from there, which is opposite over hypotenuse. So I once again get 1 over square root of 2, which when I rationalize it by multiplying top and bottom by the square root of 2, it's going to become the square root of 2 over 2. Let's do the sine of 5 pi over 4. Now that's this one down here, so this is the angle I'd be using. So you'll notice the opposite is negative 1. The hypotenuse is square root of 2. So this one, oops, it's supposed to be a 1. So this is going to be negative 1 over square root of 2. Opposite over hypotenuse. So we rationalize just like we've been doing. And I get negative square root of 2 over 2. So any multiple of 45 degrees, you should be able to find the sine, the cosine, the tangent, or the inverse functions. You should easily be able to find those using the setup that I've shown here. Here's a similar problem using the 30, 60, 90 triangle. Okay, so 30 degrees, this is going to be a 30-degree angle right here, or pi over 6 radians. And remember this triangle, so this would be the 1, positive. This would be the hypotenuse is always positive, and this is the square root of 3. So the sine of 30, 1 over 2, opposite over hypotenuse, 1/2. We can quickly verify that since that's in degree mode. I can turn my calculator and make sure it's in degrees, which it is, and I can type in sine of 30. It's going to give me 0.5. So what I'm showing you here works. Cosine of 30 would be the adjacent over the hypotenuse. That is equal to the square root of 3 over 2. Okay, pi over 6. What is pi over 6? Well, that's 30 degrees. It's also going to have sine of 1/2 and a cosine of the square root of 3 over 2. I'll demonstrate that here by changing the calculator back to radian mode rather, singular. And we'll type in the sine of pi over 6. Notice I'm using the pi symbol, not the approximation of 3.14. So it worked there. Then we'll try cosine of pi over 6 also. You'll notice I get this number, which is the same thing as the square root of 3, close those parentheses, divided by 2. We should get the same decimal. So what I'm doing here is demonstrating that this practice of drawing in the triangle around the circle, wherever it may be, actually works. I'm going to end the first video and I'll continue the second video with this, and we're going to look at a few more calculations on this particular screen right here.